It's an adventurous start. Let's hope that the presentation will be a little smoother. I'd like to thank the organizers for inviting me. I'd like to talk about recent work on polyhedral approximations in convex optimization, where basically we have a perhaps difficult optimization problem, and we make polyhedral approximations, piecewise linear approximations to some of the cost functions or some of the constraints, so as to get an easier problem. And then after we get the solution of the easier problem, we refine the approximation, and in the end, we converge to the solution. I'd like to talk about a flexible and unified framework for polyhedral approximation, which includes the classical methods that I'm sure you know, the cutting plane method, which involves outer linearization from below, and simplicial decomposition, which involves inner linearization from within. So these methods, these classical methods, are part of this framework, but there are new methods that are included and new versions or extensions of the old method, of the old methods. And the vehicle for this is duality and conjugacy. It's well known that inner and outer linearization are connected by conjugacy. If you have a function that's convex and you consider an outer linearization by subgradients, and consider the conjugate function of this f, which I call h, then the conjugate of the outer linearization is an inner linearization, where the breakpoints correspond to the subgradients here. And reversely, from an inner linearization, we obtain an outer linearization, where the slopes here determine the points of contact. So this is known, but how exactly inner and outer linearizations connect is not very clear, and I'm going to try to explain that in my talk. The vehicle is a form of a flexible and broad form of convex programming called extended monotropic programming. Here, the vector x of optimization involves components, x1 up to xm, and the cost function is additive and involves components, and each component depends on the corresponding component of x. And the fi's here are extended real-valued convex functions, and S is a subspace. Now, this problem has a dual that has the same form. It has this form here. The variables are y. The y's live in the orthogonal subspace to S, and the h's are the conjugate functions of f. So there's a full symmetry between the two dual problems, the primal and the dual. And the algorithmic idea on which my framework is based is to inner linearize some of these functions, outer linearize some of these functions, leave some other functions, some other terms unchanged, and then solve the corresponding polyhedral approximated extended monotropic programming problem, and refine the linearization by using duality and the interplay between these two. Now, the features of inner and outer linearization in this framework is that they are, first of all, combining the same algorithm. These may involve some that are inner, some that are outer simultaneously. Their roles are reversing the dual problem because of the conjugacy involved here. And the algorithm can be applied to the primal or the dual, but the two algorithms are mathematically equivalent, and they're basically two dual faces of the same coin. I published a paper recently on the duality aspects of this EMP formulation. The material is going to be in a textbook that I'm preparing. And this work was motivated by an application in machine learning, some colleagues at the University of Helsinki, Janie Yu and Juho Russi. And it's still in progress. In that application, so that you can make a connection to machine learning, we have a cost function that's of this form. R sub x, x is the optimization variables. R sub x is a regularization term. And here we have a sum of functions. Each one depends on x and corresponds to a block of data, a batch of data. So you have lots and lots of data. These functions here in our application are polyhedral, but they are very complicated because they correspond to complicated batches of data, and they are very difficult to deal with. So they are amenable to simplification by outer or inner approximation. So these components belong dependent on data. This is a regularization function which is not linearized or outer linearized. And that's the problem that we had. And we looked at the dual of this problem and applied simplicial decomposition, which is inner linearization for the dual. It corresponds to outer linearization of the primal. And it's a challenging problem, and the results have been promising so far. I'll come back to this additive cost functions a little later. So here's the outline of my talk. I'd like to talk about polyhedral approximation in general, give some terminology, review existing methodology, particularly in the area of cutting plane and simplicial decomposition methods. Then I'm going to introduce extended monotropic programming, the duality theory, and the algorithm. This is the central point of this talk. It's the algorithm. And then I'm going to discuss special cases of the algorithm, how the classical methods are obtained from it, and how you can also obtain new methods in this way. Okay, let me remind you the definition of a subgradient of an extended real-valued convex function. It's a vector y. My subgradients are going to be y's, and my primal variables are going to be x. So for a point x, a subgradient is one for which this linear function of z lies below the f for all z. And the set of all subgradients is called the subdifferential. It's denoted by this partial f of x. And the graphical interpretation is that a subgradient can be identified with a non-vertical supporting hyperplane to the epigraph of these convex functions. So you have a slope y, I call them slopes, even though they are subgradients, and you fit a hyperplane with that slope to the epigraph, and any slope like this is a subgradient at the corresponding point of contact. Okay? So the subgradient y is a subgradient at the point x where the hyperplane touches the epigraph. Now, outer linearization corresponds to approximating the epigraph of the function by subgradients, the maximum of linear functions defined by subgradients. So we have a number of points, x0 up to xk, and we have subgradients at these points, the y's, and each one of those is a function like that, and we take the maximum of those, and that defines a polyhedral. That's the general idea of outer linearization. Now, outer linearization corresponds to approximation by subgradients. Inner linearization corresponds to approximation by convex hulls. So it's a convex hull of 4 points that inner approximates a set. And more relevantly here, there's a convex hull of rays, upward pointing rays, and the convex hull of those, of the union of those, the convex hull of the union of those is the epigraph of a polyhedral function which inner approximates a non-polyhedral function. So that's the idea of inner linearization, approximating the epigraph by convex hulls of rays, given a function h, and given a finite set of points, we form these rays. We take the convex hull, and the convex hull defines a polyhedral function whose epigraph inner approximates the epigraph of h. This is just terminology. Let me just remind you also the definition of conjugacy. Given a function f, which is closed, lower semi-continuous, it's possible to take the epigraph and approximate it by half spaces corresponding to subgradients. And the intersection of all these approximating half spaces gives you the epigraph of the function. And if you consider these half spaces and you parameterize them by their slope, you get the conjugate function. So by definition, the conjugate function is like this. Given f, h of y is a function of the slope, and it's defined like so. There's a graphical interpretation here. And the conjugate provides us with an alternative view of the same function. The nice thing is that we have this conjugacy theorem, which says that the conjugate of the conjugate is the original. So no information is lost by passing to the conjugate. You can recover the original, and that's all nice and helpful. There's also another interesting relationship, which I'm going to use in my talk, subgradient duality. If y is a slope at x of f, then x is a slope at y of h. Okay? And this is an if and only if relationship. So slopes in the f correspond to points of contact in the conjugate and reversely. And finally, here's a conjugacy relation that's very important. Suppose you have a function f, this curved function here, and suppose you have its conjugate h. Suppose you make an outer linearization of f by subgradients, then the conjugate of this outer linearization is an inner linearization. Okay? And conversely, an inner linearization of some function gives you, when conjugated, the outer linearization of the conjugate. Furthermore, you have that subgradients in the outer linearization are breakpoints in the inner linearization, and so on. Finally, note that outer linearization functions are real valued or finite, and outer and inner linearization functions are cofinite, meaning that their conjugate is real valued. Okay. Okay, let me remind you also what the classical cutting plane method is. We have a number of points, x0 up to xk, and a number of subgradients. And we have this subgradient approximation. And then we minimize the subgradient approximation, this outer linearization, and then go up to the original function and pick up the slope. And we add this to the outer linearization and refine it. So as an example of the iteration, we're minimizing here the function f over this constraint set. And we have, let's say, 2 points, 1, 2, and 2 subgradients. We minimize this. We obtain this point here, x2. Then once we have it, we differentiate f. And we obtain the new slope. And we add the plane, this cutting plane, to the approximation. And we keep going, and this is the classical cutting plane method. It has many, many applications in large-scale optimization, including Danzig-Wolf decomposition and many others. Okay, now the simplicial decomposition method. This is an old method, and not much has been done with it recently. In fact, I checked with one of the original contributors, and I asked him, what has been done with simplicial decomposition recently? He says, nothing has been done for the last 20 years. However, even though people don't work on it very much, it has carved a niche in certain types of large-scale problems, including traffic equilibrium problems that involve huge dimensional multi-commodity flow problems. And there, it's really the method to use. And here's how it works. We minimize f over a constraint set. And here, we keep f untouched, but we inner linearize the constraint set. So at the typical iteration, we have some current point xk, and we have a set of inner linearization points. These x tildes are extreme points of C. And then we generate a new extreme point, and we enlarge the the approximation, and we generate a new x, and then a new extreme point, and so on. And graphically, the way we do it is as follows. These are the contours of f, and this is the constraint set, this polyhedral set. Initially, we start with a single point. We pick up the gradient of f at this point, and then we find the extreme point of C that's furthest out along the negative gradient. So we pick this x tilde 1 here. We minimize the convex function over the convex hull of these 2 points, get a new gradient, and then pick up a new extreme point that's the furthest out in this direction of the negative gradient. Now we have a bigger inner approximation, minimize f over this triangle, get the new gradient, pick up a new point, x3 here, a new extreme point, and so on. And in the end, we approach this minimizing points, approach this point, the optimal point, as the inner linearization approaches more and more the boundary of the constraint set around the optimal point. Now, this method makes no sense if the function f is if it's linear, okay? Because then it converges in one step. It makes sense only when f is a nonlinear function, but then by minimization over a convex hull of a small number of points, the problem becomes one of small dimension, and it can be solved by Newton-type methods, which are very fast. So let's try to compare them in brief: outer and inner linearization, cutting plane, simplicial decomposition. Cutting plane aims to use linear programming of the same dimension as the original problem, but with a smaller number of constraints. Okay? So it tries to reduce constraints. Simplicial decomposition, on the other hand, aims to use nonlinear programming over a simplex of small dimension, the convex hull of the finite set of points. So it's most useful for a different set of problems than the cutting plane method. So each type of method has its niches here. That's the point I want to make. Furthermore, the two methods appear to be very different with unclear connection, despite the fact that there's a general conjugacy between inner and outer linearization. You can't map them into each other. You can't say simplicial decomposition is equivalent to cutting plane or some dual form of cutting plane. They're very different in fundamental ways. However, the point I want to make later is that both of those are special cases of two methods that are dual and mathematically equivalent to each other. So even though the two are not equivalent, they are special cases of some other methods that are equivalent. Okay? So now I'm going to get into EMP and the main algorithm. So this is the problem. Again, the vector x breaks up into components, x1 up to xm. The cost function is additive, and each component depends only on the corresponding component of x. And S is a subspace, and the FIs are convex functions. An important special case of this is when the FIs are scalar functions. In other words, the components are one-dimensional. This is called monotropic programming, a term coined by Rockafellar in a 1984 book. He built on earlier work by Minty, a very elegant type of problem that means the strongest type of duality possible, as strong as linear programming duality. And Rockafellar has written a beautiful book on this problem and its applications. Now we are considering a more general problem because the x's can be multidimensional, not just one-dimensional. A special case of monotropic programming is the classical single commodity network flow problem with convex cost. Think of these x's as being flows of arcs in a network, and think of the subspace S being the circulation subspace of the corresponding graph. Then this problem becomes find a circulation within a graph that minimizes the sum of arc costs. It's a classical problem. Then we have block separable problems with linear constraints. Special case are linear programming, quadratic programming, just about any separable problem with convex cost. And linear constraints maps into this. Let me also mention that even though we have a subspace constraint here, I can easily change that to a general linear constraint simply by a translation argument. So this is not any loss of generality, but restricting the constraint set to be a subspace. The next special case is the Fenchel duality framework. Now here there are only two terms, and the subspace has this form here. There's a coupling between the x's. They have to be, the second component has to be a linear transformation of the first. And then the extended monotropic programming problem then reduces to this form, which is the classical form of Fenchel duality. Perhaps you have seen it with Q equals to the identity here. It's just a small extension. Fenchel duality has become very popular these days because of a special case in conic programming. Semi-definite programming, second-order programming, all of these are special cases of Fenchel duality where one of these functions is the indicator function of a cone, is the indicator function of a cone. Okay, the case of sum of functions, which I mentioned in connection with machine learning, where the components correspond to batches of data. Notice that this is different than this because here I have dependence on the vector x, the full vector x, and here I have dependence only on the component. However, by introducing a subspace of this form, where all the components are equal, then this problem with this subspace becomes this. Okay? So sum of functions is a special case, and there may be some additional constraints here. Note also that the f's are extended real valued, so they may embody constraints themselves. Now, the dual problem to this. It turns out to be very symmetric, identical, with just the f's are replaced by the conjugates, and the subspace is replaced by its orthogonal. And the derivation of this, I don't want to go into details, but it's very simple. What we do is we convert the problem into an equivalent problem by introducing some auxiliary variables z, zi, which we make equal to xi. Now, this defines a linear constraint to which we can assign a Lagrange multiplier, form a Lagrangian, and then minimize over x and z. And then after you do that, you obtain this dual function of y, of the Lagrange multipliers. But now you exploit the separability here. So the minimization breaks down into components. And then what comes out are the conjugates of the fi's. And also there's a subspace constraint coming from the inner product here, the unconstrained optimization with respect to the x's. So that's the dual problem. There's also a sign change. So the optimal value of this is minus the optimal value of that. They're not equal, but they are just an inversion of sign. So these are the two problems. And now let me mention duality conditions. I mentioned earlier that Rockafellar's conditions are very powerful for the case of where each component is one-dimensional. Now, if each component is multidimensional, the optimality conditions are not quite as strong, but still they are fairly strong. And there's a certain vector sum condition, which is in my paper, which involves something called the epsilon subdifferential of this function here. And if the vector sum of the orthogonal complement of S and this epsilon subdifferential is closed, vector sums of closed sets are not necessarily closed. But if they are closed, then you have strong duality. And there's a special case, there's some interesting special cases here. Assume that each one of these f's is either real valued, or is polyhedral, or it's essentially one-dimensional, depends on only one variable, or its domain is one-dimensional, then you have Q star equals F star, and then there's a dual statement. The point I want to make here is not so much the details of this condition, but rather that there are strong conditions and that guarantee strong duality, and that and ordinarily you can expect it. It's rare that you would not have strong duality between the two problems. The more interesting conditions for our purposes are necessary and sufficient conditions for optimality. This condition says that X star and Y star is an optimal primal and dual solution pair if and only if they are both feasible and the Y's are slopes at the axis of the corresponding components. And there's a symmetric condition where this is inverted by subgradient duality to give this. So for the dual EMP, you get this, but these two conditions are the same. The two problems are the same. Now, our algorithm is going to be exploiting this condition. We're going to be getting feasible x's and y's, but we're going to be trying to enforce this subgradient condition by adding more and more, by refining the polyhedral approximations. So let me formally define outer linearization. I think I have defined it already enough. An outer linearization of a function f is defined by a finite set, just a finite set of dual points, a finite set y. I use lower bar for outer linearization, and it's the maximum over these linear functions here, where x of y are the points of contact of f when y is a subgradient. Okay? But rather than remember this definition, it's easier to remember a picture. We have capital Y is a finite number of slopes. We fit those slopes to the epigraph of the function, take the maximum, and we obtain the outer linearization. Note that an outer linearization is always real valued. Okay? It doesn't have infinities. An inner linearization is similarly defined. For a given f function, we consider a finite set of breakpoints. Okay? We consider this rays. Take the convex hull. It defines a function f over bar, and that's the inner linearization corresponding to this finite set of breakpoints. See, the finite set, there are 3 points here in capital X. And there's a more complicated definition in terms of a convex hull, but we're going to skip that. Now, here's the algorithm. We have the extended monotropic program here, and we partition the indices. The blue indices are going to be outer linearized. The green indices are going to be inner linearized, and what's left is going to be left untouched. So at the typical iteration, we have a blue outer linearization that is a finite set of y's, and an outer and an inner linearization, a green linearization, defined by corresponding breakpoint sets for each a in this index set. And now we consider the polyhedral approximation to this problem, defined by the blue approximations and the green approximations. We solve this problem, find an x hat and y hat that are optimal and dual pair, and now we enlarge the sets x and y by differentiation. For each blue set, we add a slope to y, where this slope is obtained by differentiating the corresponding component at the solution, the corresponding solution term. Similarly, for the green indices, the inner linearized indices, we just revert, again we do differentiation, but we reverse the order of differentiation. We differentiate the conjugate instead of the original. Of course, there is subgradient duality, so you can reverse this and you can reverse that if that's convenient algorithmically. And that's the algorithm.
Is there some interpretation of the minimum of this approximation in terms of the original problem, like lower or upper bound?
If you have both green and blue, there's no specified direction up. If you have only blue approximations, then it's approximation from below. Only green approximations from above, but if you have a mixture, there's nothing you can say.
So what you can gain with the mixture?
Well, for some problems, it's easier to do, for some components of the cost function, it's easier to do inner rather than outer linearization. For example, in cutting plane methods, you may have a cost function, and you may have a constraint set. And it may be easier to just outer linearize the cost function and inner linearize the constraint set. Okay? It may just be more convenient to do that. It's an extra flexibility that you may or may not be able to use, but it's there and makes it broader. Okay, now let me explain the enlargement set, the enlargement step. Remember, we have this approximation, and we solve and we find an x hat, y hat that solves the approximation. Now, for every outer approximated function, we want to add a new slope. So we have the corresponding component x. Here's the corresponding slope y hat. And then we go up here, and we pick up a subgradient of this function. And it's not a flat subgradient, okay? It's just a subgradient that happens to be at this point. And we add this to these two slopes. For the inner function, it's a different kind of process. We find x hat, and we have the slope y hat. And these solve the approximated problem. And now we find a new point x tilde such that it has a subgradient, it has a slope equal to y hat. Okay? And then you form this approximation, find another function, and then fit again, and so on. It's reminiscent of simplicial decomposition, if you can remember that picture. Now let's talk about the duality here. We have this approximation of the original problem. If we dualize that, this is an EMP. It has a dual, and the dual involves the conjugates of this f, this blue f, and this green f. And the dual is denoted by h. The dual of fi is hi, but now it becomes a green function, because remember the conjugate of an outer is an inner. And similarly here, the conjugate of a green becomes a blue. And you can solve either this or that, or solve them simultaneously, whatever is convenient for you. For a given problem, it may be an algorithm. There may be an algorithm that favors just solving this, or an algorithm that favors just solving this, or an algorithm that solves both simultaneously. So in the dual, the roles of inner and outer linearization have been reversed. And the choice of primal or dual is just a matter of computational convenience. Does not affect the algorithm. Mathematically, the two are the same. The primal and dual sequences produced are exactly the same, no matter which one you solve. So regarding the solution of the approximation problems, in some cases, you may use an algorithm that simultaneously solves the primal and the dual. In monotropic programming, almost all the algorithms solve simultaneously the primal and the dual. In network flow problems, that's certainly the case. Then you would have simultaneously at the end of the algorithm the x hats and the y hats. In other problems, it may be preferable to focus on the solution of either the primal or the dual, and then after solving the primal, you can refine the approximation by differentiation. You can go into the enlargement step and differentiate. And this may be easy. It is easy in the cutting plane method. You just find a subgradient at the current minimum point. But it may be non-trivial, which happens in the simplicial decomposition method, where you have to solve a substantial problem to find the enlargement. You have to find a new extreme point. And finding a new extreme point means solving a linear program. It's not as simple as differentiation. However, you have the subgradient duality that may be useful. And note also that every pure outer linearization method that doesn't have any linear linearization, such as, for example, cutting plane, is equivalent to some pure inner linearization method, such as simplicial decomposition. Equivalent in a mathematical sense. How much time do I have? Really? Okay. So let me talk about special cases. Okay, how the classical cutting plane method maps into this framework. The ENP equivalent for this problem here, the ENP equivalent is to introduce the indicator function of the constraint set as a second function, and to introduce a constraint that x1 and x2 must be equal. So this is the subspace constraint, okay? So there are just two functions, two components, and this subspace constraint. And in the classical cutting plane algorithm, we outer linearize this f, and we leave this unchanged, okay? So the approximating ENP has this form, where f has been replaced by its blue approximation. And capital Y is a finite set of subgradients of f that have been obtained so far. So it's the method that I showed earlier. I have I outer linearize just f. I keep C unchanged, have a finite set of subgradients, minimize, get x hat, get a new subgradient, and keep going like this. So that's the special case that corresponds to cutting plane. The special case that corresponds to simplicial decomposition for the same problem is a little different. Again, the EMP equivalent is like this. This is the indicator function of the constraint set. It's the second component. But here, we inner linearize the constraint set and keep f unchanged. Okay? And then the approximating problem has this form, where C bar is a finite point convex hull, which inner approximates C. And the enlargement step involves using, after you solve the primal approximating problem, you have to solve the dual. Well, if you work it out, the dual optimal solutions are of this form here, where y hat is a subgradient at y hat is a subgradient of f at x hat, such that minus y hat is in the normal cone of this polyhedral approximation. Now, in the classical case, f is differentiable, and y hat is very simply obtained by this condition. In the non-differential case, which is new actually, you have to do some computation here to find not just any subgradient, but also one that belongs to the normal cone of this polyhedral set. And that it's more complicated than just differentiating. And now, after you obtain an extreme point of the constraint set, after you solve this problem, then you find a new extreme point by this minimization here, which in the case where C is polyhedral is a linear programming problem. The point I want to make here is that the classical methods are special cases involving this problem here, and either inner linearization of this or outer linearization of that. Okay, it's a complicated figure. That's why it took so long to load. Okay, this shows simplicial decomposition for the case of a differentiable function. I explained this earlier. You obtain extreme points by going in the direction of the negative gradient. This is a depiction of simplicial decomposition for non-differentiable cost function that has these level sets here. And here, given this inner approximation, you find a subgradient of the cost function at this point that's also in the normal cone, such that minus that is in the normal cone of the convex hull. Now you have this y hat. You go as far as you can in the direction of minus y hat to obtain an extreme point, and that's the x tilde that enlarges this current approximation. Get a new subgradient that's in the normal cone of the approximation, go in the direction of minus that, and you obtain the optimal point here. The reason being that both f and c are polyhedral. And this is a generic property. If everything is polyhedral, then you get convergence in a finite number of steps. The reason being that as you expand the polyhedral approximation, eventually you're going to be adding more and more points and get the original. Okay, let me skip this slide because we're running out of time. This is the case where you have the minimum of two functions with a common dependence on x. And there's a figure to show the duality between inner linearization. You inner linearize one, corresponds to outer linearizing the other in the dual. And this is an insightful figure if you have some time to study it. And unfortunately, we don't have time to do that. So let me say a few things about convergence. Convergence is a little tricky. It's not as simple as you might think. And in fact, I'm still working on it. Let's distinguish between the polyhedral case, where all outer linearized functions are finite polyhedral. Finite meaning real valued. all inner linearized functions are cofinite polyhedral, meaning that their conjugate is finite. And let's also require that the new refinement points that you add to the polyhedral approximations are elements of the finite representations of the corresponding Fi. This being polyhedral, they have a finite representation. So what you add, we require that they are part of this finite representation. And here's the convergence result. The algorithm terminates in a finite number of steps with an optimal, primal, and dual pair. And this is what a special case that I showed earlier for the case of simplicial decomposition. And the proof is relatively simple. At every iteration, there are two possibilities. Either the current solution of the approximating point is an optimal primal dual pair of the original, or otherwise, one of the approximations is going to be strictly refined. But there can only be a finite number of refinements. Therefore, you're going to terminate in a finite number of steps. So once you establish this fact, then it's immediate. In the case where you have, and then there are convergence results about the pure cases. A pure outer linearization case is one where there are no inner linearized functions.
There's no way to, okay, so I was hoping there would be some way to look at, for example, cutting plane methods that people use for solving integer programs as special cases of some of these.
Well, if you introduce this as part of a branch and bound scheme, for example, then it's possible, but then that takes us into a somewhat different domain where the approximations themselves and the algorithm that you use are not so important. What's most important is that you do the relaxations in the right order, and you select cutting planes to basically.
So did you have an example where you applied one of those special cases to show a gain with the other methods in practice?
Well, the one example where we have some experience is this machine learning application, structured prediction. And I think the most appropriate person to answer this question is Jenny Yu, who is here in the audience. So you can ask her about the details of the computation. Computations appear to be interesting, and they solve indeed very, very large problems. There are competing methods, of course, and it's very hard to compare these methods because the instances, there's no standard set of test problems that I know of. And it's very difficult to make comparisons. However, that the methods work, there's no question. In fact, they have been tested on very, very large scale problems.
What scale?
Well, it depends how you define scale. Number of variables or number of constraints. The number of variables is relatively small, but the number of constraints is huge. Jenny, what's the number of variables that we have? Can you give a sense of scale?
Well, I can try to hundreds of parameters with the constraints are exponential in the size of output space, so they can go. There are many controls. Controls in the algorithm, so that's how your unit per iteration, probably your solving wouldn't take place. So it would take a long time.
Yeah.
Following up on that earlier question about integer linear programs, and again, if you take the context whole of all the integral string points, wanting to optimize over that, let's say a linear function even. So doing an outer approximation is, at least in theory, feasible. You can use Gomeri cuts, for example, right, to find always a new hyperplane to add in to separate your current solution. But inner approximations, I haven't been able to figure out how to find the next integral point to add in.
Yeah. I really don't, because I haven't looked at the method in this context. There are many, many different contexts, because the method is so broad. There are many different contexts that you can look this at. And integer programming is one, but I haven't looked at that. And so I can't really say.
Can your approach help in special cases where the function can be approximated, let's say, with a polynomial number of breakpoints and then inputs, or can you see it helpful on those?
That question may be relevant in connection with rate of convergence issues. And I haven't looked at that. Yeah.
I also have one question.
Yeah.
So in the dual case, you have these bounds, right? Like in this cutting plane method, in the original cutting plane method, as well as in this dancing water decomposition, you have upper and lower bounds at each iteration. And you can use this to implement a convergence check. How can you implement a convergence check?
For special cases, you certainly can, but I haven't thought of a general method for implementing a convergence check for the pure cases. Okay, you obviously get a lower bound from the minimizing the outer approximation, and you get an upper bound by picking up the cost function, the value of the cost function at that point. So you have upper and lower bounds in that way. But one of the difficulties here is that in order to get an upper bound, you can't just pick up the value of the function at that point. They also have to satisfy the subspace constraint, okay? So that becomes a complicating factor, which in the case of the cutting plane method and the dancing wood decomposition is easily resolved because of the special structure. But in general, it may not be so easy.
So you give this as an example certain types of network flow problems. So do we know whether these approaches from extended monotropic programming how they compare to, for example, combinatorial approaches to such problems?
Yeah, we're talking about continuous network flow problems without any integer constraints. Just finding a circulation that minimizes the sum of arc costs. And the arc flows, rather. The arc flows are continuous. Now,
there's some discretization approaches that you can take as well, and then still use combinatorial.
The most efficient algorithms for continuous network flow problems are variants of primal descent or dual descent or maybe primal dual out of kilter. It's hard to beat this kind of methods. However, at least for linear costs. Now, they're extremely fast algorithms when the costs are linear or piecewise linear. Now, these methods can capitalize on this. You can convert a nonlinear network flow problem into a linear network flow problem by approximation, which can be solved with extremely fast algorithms. So I would expect that this type of method would be very effective for nonlinear network flow problems. And I don't know of any other discretization methods that would be effective, but maybe there are.